This time our topic is causes and effects. These are among the most difficult things to study, but they're important topics for us. In social work, we're interested in the causes of various outcomes. We're interested in natural causes and in the roles of risk and protective factors in bringing about outcomes. We're also interested in the effects of various interventions, and this brings us to program and policy evaluation research. So to begin to think about cause and effect, we might start with logic models and theories of change. These are useful because they make our assumptions about relationships between variables, about causal inference, more explicit. Logic models and theories of change can also be used to support program development and implementation. And they guide the development of research and evaluation. They can be used to refine underlying theory and structure of service delivery models. So let me show you some. Logic models are typically structured in this way, where you have a series of inputs, that's sort of resources going into an intervention, activities, outputs, what happens immediately after, outcomes, what results you see, and perhaps impacts, which are longer-term results. So here's a logic model template that's available on the web. You can see the URL at the bottom. Just sort of a generic logic model format that you can download and use, showing you examples of inputs, outputs, and outcomes. And here's a completed logic model for an example. This one is about protecting vulnerable populations during disasters. So you see they've described the situation on the left. They've described certain priorities that they have for protecting vulnerable populations, what they invest in terms of inputs, what kinds of outputs they expect to see, what they can do, who they can reach, and what kinds of outcomes they would expect in the short, medium, and long term. And at the bottom you see that they've talked about their assumptions and external factors that they expect to affect this chain of events. And this all provides a very nice schema to represent how they're thinking about how their activities relate to outcomes. So if you're evaluating any part of this program, you have a sort of a blueprint to work with that lays out the thinking about why certain activities should relate to certain outcomes. Now, a theory of change is a little different. Theories of change have less common or standard structure than logic models, but they generally seek to graphically portray the change process for clients or other targets of service in relation to activities, the various changes that are thought to occur in response to those activities, and the eventual outcomes the intervention is designed to accomplish. So a theory of change is often completed in a backward fashion, starting with the outcomes one hopes to attain and specifying the preconditions and supporting activities that reflect a theorized pathway of change. But again, like a logic model, you're laying out assumptions behind causal relationships. So here are two theories of change, both looking really at very similar issues. Just showing you that there's a little more flexibility in the structure for these models. But these are basically, flowcharts that show hypothesized causes and effects. On the left, you have a conceptual framework of the influence of household and maternal foods insecurity on childhood health outcomes, showing that this model starts by considering household and maternal characteristics as causal factors that influence household food insecurity. And then you see that household food insecurity is thought to affect maternal or child or caregiver insecurity, and that's also affected by moderators. And household food insecurity affects pregnancy outcomes. And then down the road, they're looking at childhood psychosocial outcomes, and they specify some childhood diet and eating behavior, and child physical outcomes. And the authors show in this graph how they think the independent and dependent variables and moderators relate to each other. On the right, you have a different theory of change, looking at household food insecurity as a mediator of the influence of poverty and other factors on child development outcomes. Now, I don't expect you to memorize any parts of this, but just to see what some of these theories of change look like. So here, the causal factors are shown in more reciprocal relationships with each other. So they look, for example, at the relationship between poor health and household food insecurity as a reciprocal relationship. The arrows go both ways. So poor health could increase household food insecurity, but also household food insecurity could increase poor health. And the same for poverty, livelihood strategies, and management strategies. And they've taken very different variables into account here in this model. So suboptimal nutrient intakes is a new variable, household stress another one, and then the outcomes that they're interested in are caregiver mental health, child psycho-emotional problems, and child development outcomes. So they're looking at those as sort of short, medium, and long-term outcomes. So one of the nice things about theories of change is that they can be tested empirically. And here's a different theory of change with an empirical model. So this is on factors that affect human capital return on investment, ROI, return on investment. So the causal model suggests that employee engagement is predicted by base pay, and that relationship is positive. So you see the arrow from base pay to employee engagement is associated with a coefficient. This is a little bit like a correlation coefficient. Not quite, but almost. It's positive. So the higher base pay leads to greater employee engagement. Similarly, benefits seem to have a positive effect on employee engagement. And employee turnover is negatively associated with employee engagement, and also with the ultimate outcome, return on investment. They've also modeled relationships between training and development and employee engagement, seeing that is a positive association in their data. And employee engagement, training, and incentive rewards are all positively related to human capital. Now, here, these coefficients are obtained from empirical data, so that there's actually evidence for this model for the relationships between these variables. I'm not sure if they've fully explored whether there could be reciprocal relationships, back and forth relationships between some of these variables. But this shows you what you can do with a theory of change. Now, the direction of causation is something to think about. We have here modeled a unidirectional causal model. Everything is going in one direction, from the cause to brain development to neuropsychology to behavior. But in our world, these sort of simple linear causal models often are inadequate. So here below you've seen a bidirectional causal model with the same variables in the model, suggesting that in addition to this main pathway, behavior also affects brain development and can become a causal factor. And that's a more accurate model of what we know about human development. So let's think about relevant studies of so-called natural causes. They're useful for identifying potential causes of unintended effects and for studying causal factors that cannot be easily manipulated. And I want to talk about two kinds of studies that are often used to do this. Case-control studies compare cases with and without the outcome of interest. And then they look, often retrospectively, back in time for differences in prior exposure to risk or protective factors. So again, you're beginning with the outcomes and looking back to see if you can identify factors that differentiate groups of people with and without those end conditions. So case-control studies are actually the method that was used to discover the link between cigarette smoking and lung cancer. The method was they looked at people with and without lung cancer, and they looked back in time to see what factors differentiated those two groups, and they consistently found that people with lung cancer were much more likely to have been cigarette smokers. Cohort studies are actually better designs for this purpose because they begin with data on exposure to risk and protective factors and examine the future likelihood of outcomes of interest. So they're following people over time, and their data on risk and protective factors is generally more accurate than the data you'd get retrospectively in a case control study. So here's an example. Does the MMR vaccine cause autism? Well, the evidence for this link, for this causal link, comes from one study, famous study by Wakefield and colleagues, published in 1998. This is a report on clinical observations of 12 children. The report was retracted after the British Medical Board found evidence of false statements, fabricated data, and other ethical violations. The report is 175 pages long, and it suggests that this was a real fraud. On the other hand, evidence against this link comes from two retrospective cohort studies, each with more than 500,000 children in Denmark, where they compared vaccinated and unvaccinated children and looked at rates of autism. They found no differences between vaccinated and unvaccinated children in terms of autism. And then there's a systematic review and a meta-analysis of 10 retrospective cohort and case control studies conducted in 5 countries with a total of 1.25 million children, showing, and here's the headline in the article, that vaccines are not associated with autism. This is a forest plot showing the relationship between vaccines and autism in each of the studies included in the systematic review and meta-analysis. So each line in this graph is a study. So here's Madison et al. 2002. You see an odds ratio close to 1, which is no difference. You see the confidence interval and the significance level. In this forest plot, 1 is the line of no difference, so an odds ratio of 1 means that the rates of autism are identical in the vaccinated and unvaccinated groups. And most studies have odds ratios that are really close to that. There's one study that finds some difference, but these are confidence intervals. The lines on either side of the dot in this forest plot are confidence intervals. And as long as the confidence interval crosses the line of no difference, then the result is not statistically significant. So you find that none of these studies found a significant relationship between vaccines and autism. Okay, so how do you interpret this evidence? What do the odds ratios mean to you? Think about what they mean. What are the confidence intervals? This is the lower end to the upper end. What do the p-values mean? And how do you interpret this data? The weight of the evidence shows that the MMR vaccine does not cause autism. We also are interested in evidence of intervention effects. And we think about this in a couple of ways. Efficacy refers to the effects of an intervention under ideal conditions. So in a lab or a university clinic where we have a lot of control over what goes on. But as social workers, we're often more interested in effectiveness than in efficacy, because we're interested in the impact of interventions under real-world conditions, where things can go wrong, people can drop out, the treatment can be provided in less than ideal ways. So this evidence of intervention effects is not necessarily more important than other types of evidence, but it does matter. We do care about effects because we know that good intentions can have unintended consequences and even harmful effects. And there's good evidence for that, particularly in the Scared Straight and DARE programs. Good intentions, harmful effects. More generally, policymakers, practitioners, and consumers want to know what works and what doesn't. But I would argue that what works is not the right question, because interventions don't just work or not work. That's a false dichotomy. The most effective interventions don't benefit everyone, may not result in improvements on all relevant outcomes, and can also have unintended consequences. So what works best for whom is a better question to ask about intervention effects, where we're looking for improvements or benefits of an intervention compared with other treatments, or less treatment, or no treatment. So we call these things relative effects, dose effects, and absolute effects. We also want to be looking for possible side effects and unintended consequences. Causal inference, which is what we're talking about here, the ability to establish a link between a cause and effect, requires three conditions. The first is correlation. The cause, we usually represent it as X, has to be correlated with the effect, Y. They have to be related. If they're not related, there's no cause. They have to have time order. The cause has to come before the effect. And we have to eliminate other plausible explanations for the relationship between these variables. And these other plausible explanations for causal inference are called threats to internal validity. So we talk about internal and external validity in research design. Internal validity refers generally to the integrity of the study. In terms of causal inference, internal validity is the extent to which a study provides unbiased tests of causal hypotheses, whether it eliminates confounding factors or other plausible explanations. More generally, internal validity is the extent to which a study adequately answers its central questions or tests its hypotheses. So internal validity is about within the study design, how well did it do in answering questions or testing hypotheses. External validity is almost synonymous with generalizability. It refers to the extent to which results from a study apply to other samples, settings, and points in time. We're going to come back to external validity in a couple weeks. But now the topic is internal validity because this has to do with threats to causal inference. And the threats to internal validity are issues that could explain apparent changes or difference over time, for example, between pre-test and post-tests, or between groups, between treated and untreated cases. So if we want to suggest that changes happened over time, we have to take into account certain threats to internal validity. And if we want to suggest that changes happened because a group was treated or not, we have to take into account other threats to internal validity. So as an example here, placebo effects are very real. When people take placebos, they expect to feel better. And that expectation itself can affect people's reports of their sort of later states or outcomes. It doesn't mean that the placebo actually had an effect. So here are the threats to internal validity. I'm going to talk about 8 of them, and this is the first of 2 slides on this. So these are threats to the idea that changes over time can have nothing to do with the intervention. So the history threat to internal validity, as it's called, means that external events outside of the study, can affect outcomes. So political, economic, cultural changes, changes in the family, in the peer group or reference groups, all of those things can affect outcomes. Again, human behavior, human experience is multiply determined. So we can see changes in outcomes that occur but have nothing to do with the intervention of interest. So here's an example. A wonderful former student of ours in social work was studying the effects of home ownership versus rental on child development outcomes among low-income families. And she assumed that home ownership accompanies pride and perhaps better family functioning and would have a positive effect on child development. But she was conducting this study when the housing market crashed. And because of that external event, many of the low-income homeowners in her study were far worse off than renters. Now, that doesn't mean that home ownership itself caused negative outcomes. There was something else going on outside of the study that had a dramatic effect on families and children. So maturation is the second threat to internal validity, and it means that the natural growth and development of human beings affects outcomes, quite apart from any intervention or study that they're involved in. So, for example, vocabulary tends to increase over time, with or without intervention, certainly among children. So comparisons of a child's vocabulary at the beginning and the end of the school year tells us nothing about the effects of schooling on vocabulary. So to look at the effects of schooling on vocabulary, we'd have to have a group of schooled and unschooled children and follow both groups over time. Selection bias is another threat to internal validity, and it is also called differential selection. It means that people who choose to participate in a treatment are often different from those who do not choose to be involved in the treatment. So when people are self-selected or selected by others to participate, they may be quite different from people who don't choose to participate in terms of their motivations, their interests, and other time commitments. So comparisons of people who do and don't participate in a program don't tell us anything necessarily about the effects of the intervention, because those people could have been different to begin with. A fourth threat to internal validity is called testing. It means that we learn from a pretest. So if we take a survey, we are paying attention to the kinds of questions that are asked, and the act of taking a pretest can sensitize us to certain information. We can become sensitive to the interests of researchers and pay more attention to those interests in the near future. We also get practice in taking a pretest. So improvements on a pretest are common. When you compare pretest and post-test scores, there's often improvement even in the absence of intervention. Other threats to internal validity. Instrumentation. So this refers to the unreliability of measures. If outcome measures are not reliable, they're inconsistent, that can account for apparent changes over time or between groups. So in order to detect change over time or between groups, we must have reliable measures. Another threat to internal validity is called statistical regression, also known as regression toward the mean. This refers to the problem that extreme scores, either unusually high scores or unusually low scores, tend to move toward the group average over time. The reason for this is that extreme scores are sometimes flukes, they're sometimes errors, and the real value is closer to average. So for example, children with very low reading scores at one point in time are likely to have higher scores when they're retested. And similarly, children with very high scores are likely to have lower scores when retested. So changes in scores don't necessarily reflect intervention effects. Another threat to internal validity is differential attrition. People who drop out of programs are not representative of others. They have reasons for dropping out. That's what makes them drop out, and that's what makes them different. And dropping out can alter the group composition. So, for example, people either continue in an intervention or they drop out, again, for specific reasons. Maybe they have or don't have the time, energy, or resources needed to participate. Maybe they like the program or don't, feel that they're benefiting or wasting their time. So in most studies, dropouts tend to have fewer advantages and more barriers than people who complete treatments. So dropouts and completers are different. Another threat to internal validity is called contamination or spillover. And these are the spillover effects from treated people to other people. So for example, if I'm providing an intervention to one group and not another, the intervention materials, lessons, and advice can be shared to non-treated groups, and that's a spillover effect. So here's a page that summarizes the threats to internal validity that I just talked about, all 8 of them. Now, how do we control for threats to internal validity in studies of causal inference, especially studies of the effects of interventions? Well, we set up what's called a counterfactual model. Now, counterfactual means against fact. It's really what would have happened if something else. So to identify treatment effects, we really want to know what would have happened to the people who received treatment if they had not received treatment. What's the effect of the treatment? We want to isolate the effect of treatment from all threats to internal validity, but we cannot do this. We cannot have a parallel universe in which one group of people is both treated and not treated at the same time. We can't do that directly. So what we do is we approximate the counterfactual model using multiple groups, some people treated, some people not treated, ideally very similar groups at the beginning, and or multiple observations before and after treatment. So that setup looks like this. So we typically describe research designs using this kind of notation. We have one group that received O, an observation pre-test at one point in time. It received a treatment, X, and it received an observation, O, after treatment, the post-test. The other group only receives the pre-test and post-test, no treatment. So we can measure how they start and how they end, and if the treatment is effective, we should see that in terms of difference at post-test. Designs for causal inference and looking at treatment effects use this logic. If random assignment is used to create 2 groups that will be compared, then the study is called a randomized or true experiment. If not, the next question is there a control group or multiple measures? And if the answer is yes, there's either a control group or multiple measures, pre and post tests, then we call that a quasi-experiment. If there is no control group and no multiple measures, this is called a non-experiment. So non-experimental designs include what's called single group post-test only designs. One group, no pre-test, just treatment and post-test. Single group pre-test and post-test designs. Again, one group but with a pre-test. Or what we call static group comparisons. 2 groups, no pre-test, just post-tests. So, which threats to internal validity remain in each of these designs? Which threats to internal validity remain in the first design? How about the second one? And the static group comparison? Okay, quasi-experimental designs again have multiple groups and multiple observations. So here is a static group comparison, 2 groups that exist naturally, with information on the baseline differences or equivalents at pretest. So both groups get the pretest, one gets treated, they both get the post-test. Which threats to internal validity remain? If the groups are self-selected, selection bias is a clear threat to internal validity because the groups might have been different at the beginning. Now we can test that, but we can't change it. Quasi-experimental designs are also known as non-randomized studies. The strongest quasi-experimental designs, the best designs to use for causal inference, involve 2 or more parallel cohorts, that's groups measured at the same points in time, with design controls or statistical controls for baseline differences between groups. So design controls, for example, means creating matched pairs, and then within each pair, giving one the treatment and the other no treatment. Statistical controls are post hoc, after the fact adjustments using statistics for differences in baseline. That's generally not as effective as design controls, matching designs, for example, in minimizing threats to internal validity. So the counterfactual model in research design. We want to ask, when we're looking at an evaluation of an intervention, how well does the research design approximate the counterfactual model? Or in other words, how well does the research design control for threats to internal validity? And in answer to the questions I asked you just a little while ago about which threats to validity remain in which designs, before and after comparisons alone don't account for history, maturation, testing, or statistical regression. All of those threats to internal validity can account for change over time. And multiple group comparisons by themselves don't account for selection bias, differential attrition, or contamination. Differences between groups could be due to these factors. So across the board, randomized controlled trials provide the best, most reliable and valid approximation of the counterfactual model. And there is a lot of empirical evidence for this. So how do randomized controlled trials work? Well, the idea is you find a pool of people who are willing to participate in the study, and randomization should create equivalent groups. So simply by randomly assigning people to one group or another by lottery, random selection, we should have two groups that are statistically equivalent on virtually all characteristics at baseline. So the groups are observed at the same points in time in order to control for most threats to internal validity. Exposure to different treatment conditions should account for any observed differences between the groups in terms of outcomes. Here the illustration is a basic randomized experiment in looking at back-to-work programs. So you split the group into two using random assignment. One group gets an intervention, the other doesn't, and the outcomes here now are whether people are looking for work or found work. You'll find some successes in both groups, but if the intervention is effective, there will be more successes in the intervention group than in the control group. So for randomized controlled trials to work, we need large enough samples to ensure that their groups are equivalent at baseline at the beginning. And this design prevents threats to internal validity that can occur with differential attrition. So what's going to happen if some people drop out and others stay in the study or in the intervention, that can change the comparability of the groups. So we handle what's called differential attrition, the fact that people who drop out are different from the people who stay, with what's called intent to treat analysis. And that keeps all of the participants in the study in the group to which they were randomly assigned. And that is a control for differential attrition. We also have to worry about contamination or spillover effects. So what if the people in the control group actually get the intervention? So we have to be very careful to assess the kinds of intervention that people are getting. So here's what some outcome data could look like in experimental and control groups. Now the groups should be equivalent at baseline. We can test to make sure they are. They're not always exactly equivalent. And both groups are expected to mature over time, to experience historical events that may affect outcomes positively or negatively. They're both expected to benefit from testing. So those are all threats to internal validity that are controlled in this design by comparing two groups at this same points in time. So the treatment effect, the differences between the groups at post-test, should be due to treatment effects. So you see that both groups improve. We assume that improvement in the control group is due to maturation, history, or testing. And then the improvement in the treatment group over and above the outcomes of the control group can be attributed to treatment effects. So with non-equivalent comparison groups, we have different starting points. And that causes a little bit more complexity in understanding the outcomes. So what if the treatment group actually is better off at the beginning? Again, we expect both groups to mature, to experience historical events, benefit from testing, and so forth. So in this case, the counterfactual, the estimated treatment effect, looks at the rate of improvement we would expect in the treatment group compared to the rate of improvement we actually saw. So here the treatment effect is based on a different counterfactual model that mirrors the rate of improvement in the control group. So in a way, we're accounting for the fact that the treatment group was better off to begin with. We can also have randomized controlled trials that have more than two groups. These are called multiple arm studies. And this supports many comparisons, so this can be a very efficient design. So for example, in a multi-arm trial where you have a control group and two experimental groups, that's really like doing two separate trials. You can compare the first treatment to the control, and you compare the second treatment to the control. So we see this a lot in social experiments. There are also what are called cluster randomized trials. And these are clinical trials or experiments in which social units or clusters are randomly assigned to intervention and comparison groups instead of individuals. So in a simple randomized experiment, individuals are assigned to groups. In a cluster randomized experiment, the clusters, which could be villages, schools, hospitals, agencies, are assigned to treatment and control groups. But there is here what we call a unit of analysis problem, so that in analyzing the data from cluster randomized trials, the unit of analysis should match the unit used for randomization. So here, the number of units in the cluster randomized trial is 2. There are 2 clusters in each group, and that's what we should focus on, not the number of people. In the simple RCT, we count the unit of analysis as people. In the cluster RCT, we count the clusters as the unit. There are also what are called factorial designs that look at interactions between 2 independent variables. So factorial designs are used to examine the effects of different treatments and their interactions. So essentially here we have a randomized controlled trial with 4 groups. And the basic design is shown on the left. So we've got 2 major independent variables, and these are time and instruction, shown as 1 hour a week or 4 hours a week. And the second major independent variable is the setting, whether instruction is provided in a pull-out, pulling somebody out of class, or in class. So people are randomly assigned to 4 groups representing different levels of the 2 independent variables. And then the data, this is hypothetical data on the right, show the results for each group. And here you can see that group 1, sort of 1 hour a week in-class instruction, has the lowest rate of change. Group 2, 1 hour a week pulled out of class, does a little better. Group 3, with 4 hours a week in class, does even better. But the interaction, the combined effect of more instruction outside of class is the best result. So interpreting results, when looking at differences between groups, We want to know how much difference is really enough to conclude that the treatment has had effects. If we compare two groups, there are going to be slight differences no matter what. And the question is, are those differences the kinds of differences we would expect just by chance, just because people are different? Well, to test this, to test whether differences are real, we use null hypothesis statistical testing, NHST, to determine whether differences between groups are, we use the term, statistically significant. So NHST is similar to the setup we discussed earlier for identifying sensitivity and specificity. So if you remember from the lecture on that topic, sensitivity is the ability to detect a condition when it's present, and specificity is the ability to rule out a condition when it's not present. And remember that we talked about the absence or presence of a condition in relation to a test result, or our ability to detect the condition. And when you set up a 2x2 contingency table like this, you can classify results as being true negative, the condition is absent and our test is negative; false negative, the condition is present and the result is negative; true positive, the condition is present and the test is positive; or false positive, the condition is absent and our test is positive. In null hypothesis testing, we're doing something quite similar. But here, we call false positives a type 1 error. We're saying that something happened when it didn't. And a false negative is called a type 2 error. We're saying that something didn't happen when it did. So let's map type 1 and type 2 error onto the contingency table we use to identify specificity and sensitivity. Type 1 error, the red part of the overlapping distributions, means that we've rejected the null hypothesis, the hypothesis of no difference, when it's true. Type 2 error, the green section of the other distribution, means that we've failed to reject the null hypothesis when it's false. So let me just go back to these two distributions. The distribution that would occur if the null hypothesis is true is the range of results we could expect to find from a bunch of samples if there was really no difference in the thing we're looking for. The distribution to the right of that is when the alternative hypothesis is true. So treatment really does have an effect, and the overall result is positive to the right of the distribution that we would be expecting to find if the null hypothesis was true. These are two theoretical distributions. What we have is one piece of data from which to evaluate these distributions. And we set a decision rule that if the data fall above a certain level, we're going to say that the null hypothesis is false. If the data fall below that level, we're going to say that the null hypothesis is supported. And we can be right or we can be wrong. We can be right in two different ways and wrong in two different ways. So again, this maps right onto the setup for sensitivity and specificity. In reality, if there is no effective treatment, then the null hypothesis is true. And if we have a non-significant result, the probability of making a type 1 error is greater than 0.5, we don't reject the null hypothesis, and we correctly conclude that there's no effect. In reality, if there really is an effect and the research hypothesis is true, then if we have a non-significant result, we say that we fail to reject the null hypothesis. This is a type 1 error. There is a true effect and we have not found it. If there is a true effect and we have a significant result, We reject the null hypothesis, and that's correct. That's sensitivity. And then finally, in the bottom left part of this contingency table, if there is no effect, but we have a statistically significant result, we've rejected the null hypothesis and we're wrong. It's a type 1 error. It's a false positive. So study the setup and think about it a while. It's difficult to get this the first time. You're going to need some repetition and play with these ideas. We'll talk about this some more. The null hypothesis testing and treatment effects. So the null hypothesis means that treatment is not effective. So the difference between treatment and control groups on average, what we call the effect size, is 0. So here on the diagram on the right, I have a distribution for the null hypothesis centered on the value of 0, no difference. The alternative hypothesis means that treatment does have an effect, and the treatment control difference is going to be positive, or at least not 0. So we're testing the null hypothesis, and we have to find a pretty extreme result, something different from 0, either positive or negative, to conclude that there is a difference. But we get a result, and this line shows the result that we've got in a sample, and it looks like this data could belong to either reality, the reality in which the null hypothesis is true, or the reality in which it's false. If the null hypothesis is true, results come from this sampling distribution. And results in the red tails of the distribution have p-values, probability of less than 0.05. They're unlikely to occur if the null hypothesis is true. So results in those areas can be used to reject the null hypothesis. Now let's say here we have a difference between groups that's not statistically significant, but it's most likely to come from a real scenario in which the alternative hypothesis is true. What type of error are we likely to make here? Think about this. Are we going to reject the null hypothesis, yes or no? The answer is no, because it's not falling in the red zones of rejection. So we're going to accept that the null hypothesis might be true, and it's quite possible that we're wrong. So that's a type 2 error. Statistical power is the same thing as sensitivity. It's the ability to detect an effect or a difference when it's really there. Statistical power is affected by sample size. So small samples have less power, less ability to detect differences. Larger samples have more statistical power. Statistical power is also affected by variation. So heterogeneous samples have less statistical power. Homogeneous samples have more ability to detect difference. And statistical power is also affected by the effect size. So larger effects of treatment, for example, are easier to detect than smaller effects. Statistical power is also affected by the statistical tests that we use, but we won't focus on that. Here's why this matters. Studies must have enough statistical power to detect differences or effects. If they don't, small studies are what we call underpowered. If they don't have the power to detect an effect, what's the point of doing the study? So if a study finds no evidence of effects, you should ask, does that study lack sufficient statistical power to find the effect? If so, it shouldn't have been conducted in the first place. If a study finds no evidence of effects, and it did have the power to find effects if they were there, then that's meaningful. Let's work on interpreting null hypothesis statistical testing. This is not easy, so we'll try it a few times. when the p-value is less than 0.05, that means that there's only a 5% chance that we'd find a difference this great or greater if the null hypothesis is true. And we can reject the null hypothesis. This provides evidence of an effect, evidence that the alternative hypothesis is true. It does not prove that there is an effect. It does not prove that the null hypothesis is wrong, because we could have made a type 1 error. When the probability that the null hypothesis is false is greater than 0.05, we cannot reject the null hypothesis. We say there is no evidence of an effect. This does not prove that treatment is ineffective. And it does not mean that the null hypothesis is true, because we could have made a type 2 error, sorry. So no evidence of an effect is not the same thing as evidence that there is no effect. We could have insufficient power. We could have made a type 2 error. This logic's really important, so please read this a few times and see if you can't get your head around it. One lesson to take away from this is that we don't prove anything. We find evidence that suggests that one hypothesis is more likely than another. We could be right, we could be wrong. So there's always the possibility that we're wrong. That's why we're not proving anything here. Why does this matter? Well, we test the null hypothesis because it clearly represented by a sampling distribution centered on an effect size of no difference, an effect size of 0. It's less clear where the sampling distribution for an alternative hypothesis lies. How big should the effect be in order for us to detect it? We use probability theory to decide whether to accept or reject the null hypothesis, and this makes the decision rules transparent. Moving on to a slightly different topic, there are trade-offs between internal and external validity in research design. So here I'm showing you different study designs, and I want you to focus on randomized controlled trials versus the green circle, which are quasi-experiments. You don't need to know the specific names of those quasi-experiments, versus the red circle, which are non-experimental studies. And what this is showing is that in general, randomized controlled trials have high internal validity, meaning they control for most threats to internal validity, but they have less external validity, meaning that the results are not as generalizable as other studies. Quasi-experiments seem to balance internal and external validity better, and non-experiments might be generalizable, but they don't do a good job of controlling for threats to internal validity. Let's talk about some other designs. These are non-experimental designs that sometimes provide compelling evidence of effects. So here I'm showing you multiple baseline designs. So this setup is useful when we have introduced some intervention in different settings at different points in time. And if we can show that after the intervention, there's an immediate and clear change, and if that intervention is, again, implemented at different points in time, yet the clear change seems to be linked to implementation of the intervention, not some other historical event, then we've got evidence for a relationship between intervention and outcome. So this is a very clean example of that. Unusual to find such a clean example of multiple baseline design providing compelling evidence of a causal effect. In this example, we're looking at a measure of fish prices, and the author conducted a weekly survey of 300 sardine fishing boats. And the results are shown on the right. The vertical axis, the y-axis, shows the average market prices for sardines in Indian rupees. And what we notice here is that as soon as mobile phones are adopted in each region, sardine prices immediately stabilize. providing a strong support for the law of one price. That is, with the introduction of mobile phones, people start talking and they harmonize on a consistent price. Pretty compelling data. Let's talk now about moderators and mediators. So moderators are variables that affect the relationship between other variables, while mediators are variables that come between and explain causal relationships between other variables. So they play a more active role in a causal chain. Let me give you some examples, but first I will show you the sort of theoretical difference between these variables. Again, moderators affect the relationship between two other variables, while mediators are part of a causal chain. They help explain why one thing, an independent variable, leads to another. And confounders, on the other hand, are third variables that really explain, fully explain, the relationship between two variables. Again, let me give you some examples. Social support is a moderator of the relationship between stress and depression. So here we're showing that with low social support, stress exacerbates problems with depression. With high social support, stress increases depression, but not as much. So social support moderates this relationship. Here's an example. Again, we have social support as a moderator between stress and depression. Example of a mediator includes access to health care, which mediates the relationship between poverty and health outcomes. So here, poverty has a direct effect on health outcomes via other moderators like nutrition, but access to health care also plays a role in that poverty affects access to health care, and access to health care affects health outcomes. So here you see we have two pathways between poverty and health outcomes. One is direct, and the other is through this mediator, access to health care. It's an example of a confounder, a third variable that fully explains the relationship between two other variables. I'll use again the example of the relationship between shoe size and math ability, which is fully explained by the confounder of age. So let's talk now about critical appraisal of causal inference. And here are some central questions. How well does a study that aims to test or show causal inference control for threats to internal validity? How well does it rule out other plausible explanations? That's the main question here. And we often use the Cochrane risk of bias tool to get at questions of threats to internal validity, where each of the following items is coded as the study has a low risk of bias, a high risk of bias, or it's not clear. And a Cochrane group has identified several important issues. Selection bias is maybe the single most potent threat to internal validity. And because if there are systematic differences between groups at baseline, that can fully explain differences at outcomes. So for that, if we're looking at a study of causal inference, we want to ask ourselves, could selection bias explain the results? Another problem is called performance bias, where something other than the intervention affects groups differently. Maybe the treatment group also has some other kind of incentive and does better on outcomes. Attrition bias means that participant loss affects the group's comparability. Detection bias means that the methods of assessing the group comparisons affect group performance. So for example, if outcome measures are done and the outcome assessors know which group the participant was in and have a personal favorite group, that method of assessment could account for differences. Outcome assessors could expect that one group will do better than another, and their expectation alone can affect their ratings. And then we also have risk of bias in the reporting of results. So studies often demonstrate selective reporting of outcomes. That's another question to ask in assessing causal inferences. And then we also want to ask whether the study has enough statistical power to detect meaningful effects if they're there. We could alternatively do critical appraisal just focused on the threats to internal validity. So again, I have this slide for you showing major threats to internal validity. So we could just use this and say, well, what's the possibility that there's some history threat or a maturation threat, and so on. That's all for now. I look forward to talking with you about this.